LeetCode 29. Divide two integers isn't just about math, it's a low-level coding puzzle in disguise. Imagine environments like embedded systems or databases where multiplication, division, or modulo are banned. That's exactly what this challenge simulates. So how do we divide without the usual tools? We'll start with the basics. But the real fun begins when we outsmart brute force. All right, ducklings, time to try the most waddly approach, brute force. We'll simulate division by repeated subtraction. Strip it down to basics. Subtract the divisor from the dividend until it no longer fits. Let's see it in action. First up, edge case alert. Dividing the smallest 32-bit integer by -1 would overflow. So we catch that right away and return the max 32-bit integer. Now let's figure out the sign. We use XOR to check if one, and only one, of the inputs is negative. If that's true, the result should be negative. Since taking the absolute value of integer min value causes trouble, we cast both values to long and then safely take their absolute values. We set up our quotient as 0. This will count how many times the divisor can be subtracted and will hold our final answer. As long as the dividend is still bigger than the divisor, we subtract and increment. Each subtraction is one division step in disguise. Once the subtraction loop ends, we apply the sign. If the answer should be negative, we flip the quotient before finishing. This brute force method runs in big O of dividend divided by divisor, which gets ugly fast. If the dividend is 10,000 and the divisor is 1, we do 10,000 steps. Not great. Space stays at 0.1, but beware, dividing min int by -1 still causes overflow. So how can we avoid all those tiny steps? Let's get clever. Instead of subtracting one unit at a time, we'll subtract large chunks by doubling the divisor. Exponential bytes instead of breadcrumbs. Once again, we catch that pesky overflow case up front. If dividend is integer min value and divisor is -1, the result overflows. So we cap it at integer, max value. We check the sign of the result using XOR, same idea as before. If only one input is negative, the result should be 2. We convert both values to positive longs. This helps us dodge overflow traps and makes subtraction cleaner and safer. Next, we set up our result variable. It'll collect all the multiples of the divisor we can safely subtract from the dividend. Here comes the main loop. While the dividend is still big enough, we try to subtract the largest possible multiple of the divisor. We scale up fast. Starting from the divisor, we double it again and again, like building a ramp, until the next jump would overshoot the dividend. Once we've built the biggest chunk we can subtract, we take it out of the dividend and add the corresponding multiple to our result. After all the big bytes are done, we apply the sign. If we marked the result as negative earlier, we flip it before wrapping up. This approach is way faster. We're down to big O of log of the dividend. For 10,000, that's just 14 steps, still 0.1 space. It's a slick upgrade, compact, quick, and robust to edge cases. But we can go sharper. The doubling method still builds up from small chunks. What if we reversed it? Start big and scan down. A top-down bitwise strategy is our next power move. One last time, we catch that overflow trap up front. Integer min value divided by -1 goes out of bounds, so we return integer. Max value. We figure out the sign using XOR again. Negative result only if exactly one input is negative. Same logic, still useful. We cast both numbers to positive longs. That makes shifting and subtraction safe even when dealing with extreme edge cases. We prep our result variable. It'll collect all the power of two pieces of the quotient, one bit at a time. This time, we loop from bit 31 down to 0. At each bit, we check if the divisor shifted left fits inside the current dividend. If it fits, we add that power of 2 to the result and subtract the shifted divisor from the dividend. Like pulling out a big chunk in one move. After collecting all the fitting bits, we apply the correct sign and finalize the result. Negative if needed, positive otherwise. This method is top tier, big O of log of the dividend, just like before, but with max control and minimum overhead. For 10,000, just 14 bitwise checks. space is still O1. It's the cleanest way to simulate division without native operators. Great for interviews or systems-level code. We began with Wadley brute force. Slow, but it works. Then we leveled up with doubling. Fast, exponential steps. But the real MVP is bit shifting. Scan from the top, slice off chunks, and finish with minimal effort. It's big O log of dividend with constant space. Sleek, efficient, and battle-tested. Engineers at top companies use strategies like this when operations are limited. Now it's your turn. Where else can bit shifting or doubling replace expensive work? Keep optimizing and let your algorithms fly.